Yeah, thanks Sergey for the introduction. This is basically the thing that I want to say. So we made up this glorified title explaining what we want to do. Actually, this is, I should mention my co-authors here, thanks to them. I'm just presenting here. This is the title actually, but actually it's all about unparsers, right? So we actually have facing things in application security, so the web thing, that can be simply solved by unparsing correctly. So glad to see this year the OWASP released another top 10 list, so I can reference this here. Actually from the last time to now, the first three do not really change. So looking at those, one can see that there is number 1 and number 3, which are both injections, right? So they are no difference. Injections exist in whichever language you basically unparse. So the point is here, I mean, keeping those two things different just confuses people, right? Cross-site scripting is nothing else but injection. So the root cause here is basically that when unparsing some things, it's really difficult to correctly to do this correctly and context sensitive encoding in this case. So basically in HTML, it's really hard to spot the right encoding for the right context. To bash a little bit more about the OWASP thing and the AppSec. So basically, as the keynote already pointed out, well, doing it like we did before might be not a good idea. So basically concentrating on new things is a good thing. So basically throwing static analysis and dynamic analysis all the time against Turing-complete languages might not end up in being a well good thing. Because yeah, what could we expect from this, right? It's Turing complete, so it's not going to bring us much. And so is like this unparsing, which I noted here actually in Java, is just like, I mean, if you're just using some string concatenation, your program does not state what it's really doing there, or what it's trying to achieve. So you could not do anything about this. Or make it any better. Actually, the thing is, it's easy. That's the only point why it's used, right? So just printing it is easy, so people do. So coming from a LangSec perspective, then the idea must be to actually specify what we want to print out or unparse actually before cutting it all together. So on the other hand, it needs to be usable, right? So the average software developer just does not care about this, right? It needs to be easy as string concatenation. Yeah, otherwise they just don't care. So as I just discussed the first point, we want to solve actually those injections coming from the application security thing with LangSec tools. And now I want to tell a little bit more on how we actually try to do this, and then afterwards coming to some listings about how we actually define binary grammars, which our grammar DSL. So first, a little bit more into the problem then. So basically, what is injection? Injection, you usually have this thing where you have an attacker which is using one language, talking to a front end. This front end being a web server or so, unparsing some message into a language, and that one is then sent over to a target, mostly database. This is the classical setting. But this might be anything, right? So every two systems communicating with each other, where the target is trusting the front end, is basically prone to injection if the language supports injection, so to say. So what actually is injection? Injection means that within a parse tree, so basically, I assume always that we have something like a parse tree within the component that is basically sending the message, because otherwise I'm always screwed, right? If I don't have a structured representation of this thing that I want to send, I'm screwed at the very beginning. So having that one, basically there might be some syntax within the leaves of this parse tree that actually do not belong there, right? So from a definition of this parse tree, they should not be there because the token definition of these leaves should not allow those tokens to be there. So what we actually want to achieve is what I've written down there with some formulas, is basically that we want to ensure that those messages that we unparse basically end up in the same AST or in the same parse tree as the one which sent over the line. This is basically the one we want to have. And there's encoding actually required. So encoding basically being ripping out those characters or those keywords that are messing up basically those tokens. So I have this here as an example again to clarify. Hope you can see those arrows, yeah, right? So basically, you have this parse tree on the left, then unparse this to the string representation, and then parsing it again. And I just want to have, as I just said, the same parse tree again. So what happens if I add there some things that do not belong into this token? They get unparsed and then manipulate the parse tree on the other side. So basically, what I actually want to do is I want to detect this and basically just only detect, okay, here's an injection. How do we do this? We basically check those tokens again with a parser combinator. As we are using hammer underneath, we are basically checking those tokens there with the parser combinator, which was used or which should be used to actually derive this token, and check if this when we parse this, if this is still the same the same token type. And afterwards, we double check that there are no keywords within this one, so yeah, the parser that does not get confused. So now now we detected this, and now we want to actually automatically derive an encoding from a grammar. So basically, the challenge is you just write the language there as over there with this MCG Montecore grammar thing, and we want to extract all those keywords. Then we split those keywords, so we might not end up in some cases where some neighboring nodes within the parse tree have some parts of the keyword and end up in the same in this keyword then. And afterwards, we want to actually identify from this grammar which symbols we could use to actually create an encoding. So in this example here, there is this ID token, the only one which actually allows some more symbols, and this is why we only have there some free symbols we could actually use to create some encoding. Encoding here means that you can put some other keywords within this token, being not any more keywords. For all the others, we are screwed because we don't have any free symbols. And then actually we need to take out from those free symbols those keywords that we are having over here. So basically these parts of the keywords that do not need to be part of these symbols that we can use for encoding actually. So then we actually first choose basically we choose two symbols and do a binary encoding of all keywords. So basically we enumerate all those keywords, choose two symbols, do a binary encoding of this one. We know actually when processing the grammar how many keywords are there, so it's just deterministically clear how many keywords we have, how long this encoding might end up, and we can basically generate all this stuff. Here's an example for this very grammar, how some of those encoding look like. And we would basically choose here capital A as our escape symbol and B as another symbol for encoding here. We actually experimented a little bit with some option called CISO, which means stuff in, stuff out. So basically not only not only encoding those keywords, but all symbols which are not defined within this grammar, which means that you could basically stuff anything in there and it still ends up. So stuff anything into your parse tree, and then it's serialized and back parsed at the receiver and still ends up in your parse tree. If you just want to transfer data, this is nice. But from another point of view, is this like, okay, you actually define your grammar as a receiver. You define your grammar and state, okay, I want just expecting those kind of things to be read, and then you end up having some different things in your parse tree, which you did not specify within your grammar, which might lead to some confusion and some other kind of secondary confusions within this application then. So actually, as I already said, we used Hammer for implementation, which is called MC Hammer Coder. Actually, I guess Sergey was coming up with this name, so we had a conf call and he was like, okay, MC Hammer would be cool, wasn't it? I guess. Yeah, you're the one.
Okay, I disavow any memory.
Okay. It's the combination of Monticore, which is the framework for actually designing domain-specific languages for all those Java guys out there. And we actually integrated this with a Hammer parser backend and integrated our encoding and decoding generating for this. It's actually providing a parse tree within Java, and you could actually specify those actions in Java, ripping them all through that they are triggered by Hammer and then executed again into Java. You can find all this code on GitHub. Have fun. And now I'm going to show you a little bit more about those grammars, so those Monticore grammar binary languages, how we can define this. So basically what we have here on top is straightforward, just some tokens and some productions, so this is our starting point basically. This is what Monticore provided before. And we actually extended this by adding some binaries, some binary constructs for actually extending the alphabet for binary representations over there. So down here you can see you have these integers where you can specify in those brackets how they, if they appear, how they must appear, and then afterwards you can specify some other alternatives, so you have the idea. You can basically specify what you expect there. This is, in the end, this is translated to Hammer, so should somehow, the concept should match over there. And then we added those concepts also present in Hammer, which is offset and length fields. And actually, with these offsets, we can specify a linear function. So basically, we can, when we parse, we have this offset rule over here, and we can then, by this function over here, we can specify how this parsed value translates to the offset. We could have actually implemented this as well for the length field, which was the comment actually for the presentation right before. So we actually support kind of the same thing that we just heard about this length fields with this calc regex. So basically we name those length fields, and afterwards you can basically use this very value you just parsed, which is I hope, kind of the same thing, so we are ending up in the right direction over there. So we did some evaluation, basically some functional ones for our generated Hammer parser, which we fuzzed with Peach fuzzer, and thanks to Hammer we had no crashes, which is great. I mean, I have no clue about how to really do this right, so thanks to Hammer we had no crashes. And then we compared this to, so we threw those inputs to our parser and to DNS parser, which is bind in this way, and then our language was just the same from these samples, like the bind parser, which accepted write the same packets actually. And then we do what all those web guys do with when it comes to encoding, to actually have a look at if this is correctly encoded. We basically use those specialized fuzzers for web languages. So basically we have an HTML language with JavaScript and try to fuzz this one with ZEP, IBM AppScan, and FuzzDB. And we actually did not find something which, well, might be okay, but I hope we really did not miss something over there. And actually we compared those parse trees because actually we have different encoding than which was specified within HTML. So we came up with a generated encoding which browsers definitely do not understand, but our own decoder then does. So when we compared those parse trees we sent and those parse trees we parsed again, we did not find any differences for all those inputs. So to sum up, we have this situation where the injection vulnerabilities are still, kind of not really understood by those guys who care most. So basically the OWASP top 10 seems to be broken. And those guys should really catch up with some LangSec stuff, I suppose. We delivered here some ideas on how to actually generate some encoding if you're running a new protocol or new language and you're not building up on all those stuff that is available for the web, and you're running a new protocol, you actually want to have something that provides you these kind of encoding, and so you don't mess up those things by yourself. The last point actually so reflecting back to the keynote is basically, I mean, if we get this right, so these parsing and unparsing, if we actually get this right, we might end up in a solution where we actually can verify some things, right, and decompose security again, which would be great. I mean, like we would have been at last for the last 30 years with this would be great. So some points where one could actually work on is definitely parser differentials, which we definitely do not care about. I mean, when we have different parsers, they definitely behave differently, and this is what we did not cover in the approach up to now. On the other thing, for doing some more offense research, might be interesting to actually learn those languages that programs talk, right? So basically extracting those grammars from existing implementations and look for injections. So basically extracting those keywords and try if we can inject things over there. Might be interesting to find some things. And as I said before, I mean, we need to get those things more easily and bring this more to the heart of developers so they actually use this stuff. This would be close to my heart, so perhaps we can do some things about this. And that's it. Thank you. Some questions?
Three very, very quick points. First of all, on your early slide where you showed your invariant for the parse of the unparse, yielding the original, that's the theorem you have to prove in order to just show that your implementation is correct. It's right there. If you were working in a system like Coq, that would be what you would have to prove.
Yeah.
And then you would know, and and then you would know that the rest of it was correct. Second quick question. So you almost are doing this in some ways too well, because by getting the invariant in and out, even in the presence of something that's clearly hostile, code that's down the line and is badly written will be vulnerable, even though code that's using your technique it will not be protected by code that's using your technique. Your code will work fine regardless of what you throw at it, and then something that's badly written down the line will still receive, the embedded stuff in some token.
Yeah, basically it's just unparsing, right? It's not caring about writing a really good parser. It's right the other way around, right? So, and this is kind of the CISO thing. So if you enable the CISO mode, yeah, definitely your parser is, or your parse tree, which is generated from your parser, contains stuff that you're not want to have it in there. So this was just an option, and we actually do not enable this, just showing this.
So in fact, you might describe unparsers as deliberately not providing extra ammunition, extra computing power to the attackers, refusing to be co-opted into their execution model. But of course, other execution models exist.
The last real quick thing, you buried something that looked really, really fascinating on the last part of the last slide, which was the notion of providing programming languages with built-in reasonable representations for grammar.
Yeah, needs to be done. Yeah, if you have a good idea for this, I'm very up to getting this done. But I'm actually not sure how this really is the right thing, right? I've seen some guys writing grammars within XML things. So this might be not the right thing.
We have lots of languages with regular grammars built in. Clearly, what we're interested in here is much more general. It's with the same ease.
But the point is that if the code that deals with inputs doesn't look like the grammar of those inputs, that code is trouble. That code has no business existing, right? OpenSSL, you look at it and you see a pointer salad, right? Spattered with integer arithmetic. This is deadly. If it doesn't look like the grammar, it is trouble. We pretty much know this. So what you say, and what Lars just said, is again a corollary of that. We must make it easy for developers to make the code look like the expected valid grammar. Parser generators are that, but other means are called for as well.
Mm-hmm.
More questions?
So regarding to the bidirectional property of parsers and unparsers, I think it might be too strong for some of the parsers. So for example, if you think about a compiler which parses source code to some abstract syntax tree, and that parsing may forget the number of white spaces when creating the abstract syntax tree, right? So when you go back, you don't get a unique response.
Yeah, we skipped actually this problem. Actually, in the first implementation, we tried to actually incorporate the AST abstraction in there. But yeah, as you're right, then basically this construction of the unparser is really a tough thing. So we basically stick with the parse tree.
It's worth maybe like having this conversation with like Dean Weitzeff and Anya Vaga at Software Language Engineering later this year, because like they do the whole parsing and unparsing mega model that like talks about white space reservation and stuff like that. So they
don't want to solve it again, right?
Yeah, so I'm sure they've got some good insights there.
Yeah.
More questions? Let's thank the speaker.
Thank you.